mainly the optics. And then the first 2 weeks are dedicated for the geometry optics, or which is also called the ray optics. In other words, we are going to look into the ray propagation, how the light actually bends its directions when it enters to a different material, and also the image formation. Yeah, so by lens and the meters, so how the image are actually formed, and what is the virtual image and what is the real image, on all those stuff. And when we reach to the week 3, then we will switch our topics to the wave optics. So in the wave optics, we are going to try to explain the interference and then diffraction and then polarization, which can be only explained using this wave optics concept. All right. So, well, since this is the first week, so our topic is going to be under this geometry optics, and then we are particularly interested in the ray propagation in this week. And these are the list of the subtopics in this week, and then they are also, well, I just copied those subtopics from the LAMS contents in the chapter 1. Okay, so now we ready to start. I'm going to touch all those subtopics in this summary lecture, right? Now, the very first topic is the reflection and then refraction. We know that when a light strikes a boundary of 2 different medium, then the part of light will be reflected, and then part of light will reflect into the second medium. All right, and then in this diagram, we can find two boundaries. So we have a boundary on top of this medium B, and we have another boundary in the bottom. Therefore, we can find the 2 reflections as well as 2 refractions. Okay. Now, first of all, we can identify the reflections in this diagram. For instance, where this incident ray is reflected to the number 2, and then we have another reflection which follows number 3 arrow and then reflected to the arrow number 4. We can also identify refractions. Well, the incident light, sorry, why it doesn't work? Just 1 second. Yeah, incident light will reflect into this medium B, and then the ray number 4 now becomes the incident ray to this upper surface. Therefore, it will be reflect out to the medium A. Oops. Sorry. Yeah, medium A. And then I just mentioned that we have a different media in this diagram. So medium A and the medium B. And then what does that actually mean? What is the difference? How these materials are different in our context? Any idea? But they are different media. Yeah? Medium A and the medium B are different, but in what context? Do you have any idea? You can type your answer in the chat room. Density, very good. And then what will be the different properties? Yeah, light travels slower in the second medium, also very good. Optical density, refractive index, wavelength, very good. I'm very happy. Okay, I'm very happy to see all those answers. So they are different. Okay, in our context, the difference refers to refractive index. In other words, the medium A has its own refractive index, and then medium B will have its own different refractive index. So in our context, when I mentioned different media, that means they have a different refractive index, and then those different refractive index actually determine the wavelengths of the light in the different medium too. So we will touch about these wavelengths in the week 3. Okay. So anyway, well, again, let me reiterate. In our context, the different medium means a different refractive index, and I'm going to introduce the index of refraction later part. All right. Now, let's have a look at this diagram, which introduce a very important concept, which is the plane of incidence. So, well, sorry. This is supposed to give me some animation, but never mind. I will try to explain this plane of incidence. So in the plane of incidence, which is illustrated here, you can see the interface between two different medium as the horizontal line, and we also introduce vertical lines in this plane of incidence. And the incident ray is now then drawn into this intersection point of this horizontal line and the vertical line. And as we know, part of the incident light will be reflected and the part of light will be reflected into the second medium. Now, in this diagram, as you can see, we have incident ray, refracted ray, and then reflected ray. All those three rays are defined inside this plane, and then this plane is called plane of incidence. Okay, so this is a very important concept, and then I hope you can familiarize yourself to this one. So again, let me repeat: in the plane of incidence, the incident ray, refracted ray, and the reflected ray, they are all inside the plane. Okay, so if this incident ray coming from different angle out of plane, then you must move your plane to represent the incident plane for that out of plane, the incident ray, right? So I will have more chance to talk about this plane of incidence later part, but for now, I hope you understand that all those three rays must be inside the same plane, right? Then, well, reflection and the refraction, as you just seen in this plane of incidence, they actually change their directions. Okay, then how we can actually determine those directions? Well, we use Fermat's principle. All right, we use the Fermat's principle to identify the direction of the reflection and the refraction. And then this Fermat's principle is also known as least time principle. Okay, so let me draw some diagrams so that I can explain those the Fermat principle. So just 1 second. I'm going to switch to the my notepad. So just 1 second. Okay. Well, can you see my screen, notepad? All right, great. So let me draw some lines. So we have point A, and then we have point B. All right, and then you can come up with barriers of a path to connect those 2 points. So you can connect those 2 points with this straight line, or you can also connect those 2 points with a curved line, or you can also come up with a more complicated one. And according to the Fermat principle, the light should travel point A to B with the least time. Okay, so in other words, we must draw this straight line to connect the point A to B. All right, so this is very straightforward. Now, let me draw some new diagram. So here we again have a point A and a point B. But in the new case, where this point A and the point B are separated by this boundary. In other words, point A is in refractive index of NA, and then point B is in the medium with the refractive index of MB, and then NA and the MB are different. Then, in that case, which path will satisfy the Fermat's principle or promise the least time taken to connect those 2 points? So one possibility is still we use this straight line. Okay. Another possibility is maybe there's some other route that can, like this, which will be taken less time than this straight line. All right. And then this light bending is going to be dispersed in the context of the Snell's law. So I will come to this point later. But for now, what I try to convince you that when the light travels from point to point B, then it should take the path that will take the least time, okay, according to the Fermat principle. All right, now I'm going to go back to the lecture note. Okay, so let's move on. Now, let's first look into this law of reflection. The law of reflection states that the angle of incidence is the same as angle of reflection. And then this is the law of reflection. And then I like to highlight that when we define this angle is always measured from the vertical line to the respective respective ray. Okay, so for the angle for the reflection, you must find the angle from the vertical line to the reflection. Okay, so this is our definition of the angles, and then you should not take this angle. Okay, so this is not your angle. Your angle must be drawn from the vertical line. So this is very good. And this law of reflection is actually can be confirmed using the Fermat principle. And well, you can, so all those derivations are actually introduced in the one of the last video in this week. So please go to watch the video to do this derivation, all right? Now, well, it's time to talk about the reflection. So let me first introduce the index of the reflection. It is intuitive to understand that the light travels at its maximum speed in the vacuum. Okay, in other words, the speed of light will be slowed down in other medium, right? Then the ratio of the speed of light in the vacuum to the speed of light in the medium is refractive index, or the index of the reflection. And as you know, the speed of light in the vacuum is always larger, okay, or the speed of light in the vacuum is always faster than the speed of light in the medium. Therefore, your refractive index is going to be always larger than 1. This makes sense, yeah? So for instance, the refractive index of the water is 1.33. So index of the medium is always larger than 1, okay? And then index of the, and the refractive index of the air or the vacuum is 1, all right? Then you can also, well, rearrange this equation for the speed of light in the medium. Then you can easily understand that the speed of the light in the medium is slowed down by the amount of the refractive index. So the higher the refractive index, then the slower the light. All right. Now, I like to introduce important concept which will be very useful. You will find very useful in the rest of the course. Okay, so this is called optical path length. Optical path length actually describe the traveling length of the light in a certain medium, and when mathematically it is very easy to determine this optical path length. You just take the length of the 2 points, point A and B, and then multiply with and then times multiply by the refractive index. Okay, then you can understand that optical path length is shorter in the vacuum than glass because the refractive index of the vacuum is always smaller than any other medium. Now, this diagram actually illustrates this concept of optical path length very well. So let me just show you these diagrams. So let's assume that the light travels from point A to point B, okay? And then the point A and the point B, they are separated at a distance of length L. Now, when the light travels in the air, it does not feel any resistance. So it just travels freely, all right? On the other hand, when the light travels the same distance in a glass, then it actually feels some the resistance because the glass is a denser medium, yeah? And then this is like we work in the swimming pool, all right? So because of all the water, where our working we struggle walking inside the swimming pool. Yeah, so our speed is going to be slowed down in the water. So similarly, the light will be slowed down, and it actually feels some resistance when it travels in a glass. And then, well, according to our definition of the optical path length, you can actually determine those. So for the air, the optical path length is going to be the geometry length L times its refractive index over 1. Okay, and then the optical path length in a glass is going to be the geometry length times its refractive index. And then as you can easily see, the optical path length in the glass is doubled. Yeah, it's much longer than the air because the index is higher in the glass. And then the light actual field, it travel longer time. It travel longer distance in the glass. Now, because of these different optical path lengths, the time taken to cover the same distance in the air and the glass are also different. You can easily reach it to this equation. Yeah, the time taken in the air is going to be this L divided by C, but the time taken in the glass is going to be just double, yeah, because its optical path is going to be longer. Therefore, well, the light will experience a longer distance, hence taking longer time to travel. All makes sense. With this optical path length in mind, let me revisit this Fermat's principle. So Fermat's principle is often portrayed as a life guide problem. And then I actually have some kind of small simulation about this, the animation. So let me switch my screen. Just 1 second. Okay. All right. So you can, well, see this diagram, and then we have this lifeguard try to save a drowning person in the water at the point B. And then this lifeguard can travel faster on sand than in the water. And in our settings, this lifeguard can travel at the speed of 10, on the sand, but this lifeguard will travel in the lower speed, well, about 3 in the water. Well, earlier I introduced what would be the, I asked you what would be the least time path when the light travel different refractive indices. All right, so the one possibility is the straight line connecting point A and B as illustrated by this red line, or there might be some other optimum path which will take the least time to connect the point A and then point B. So with those settings, let me start this animation. So the lifeguard trying to reach to this drowning person, and let's see which path gives us the least time path. Yeah, well, it seems like this blue path actually guarantees the least time path, okay, for reaching to the drowning person. Therefore, we now have this conclusion. When light travel across 2 different media with different refractive indices, then the light must bend its direction to satisfy the Fermat principle, okay? So that will give you the least time path, all right? Now, with this, I'm going back to the lecture note. All right. So when it comes to the, so we now come to this law of refraction. The light travel across those 2 medium, okay, with a different index N1 and then N2. Then in order to set this the least time path, the light must bend its direction. Okay, so the propagation the direction must be changed when it enters to the second medium. And then how are we going to define, how can we determine this direction? We are going to use the Snell's law, okay? And then this Snell's law also easy to memorize, where N1 times sine theta 1 is angle of incidence, yeah, equals n2 times the sine theta 2, which is the angle of refraction. And then this Snell's law can be derived using the Fermat principle. And again, where we have this derivation using the optical path length, the definition of the optical path length in the medium A and the medium B. And the working of this derivation is also introduced in the last video. So if you want to try yourself, please watch the video to derive this Snell's law based on this the Fermat principle. Okay. Now let's say, well, you already calculated this Snell's law equation, and then you now find these angles for the reflection. But then I still want to verify whether my answer is correct or not. So how are you going to do that? Well, one way to confirm your answer is to use this kind of the second alternative way. So you can actually consider this the light bending or the reflection as the gravity force, where the heavier object will pull other object more strongly. Yeah. Therefore, in the refraction, when light enter to the higher refractive index, so the light enter from the lower refractive index to the higher refractive index, then it will pulled by this higher refractive index. Therefore, the light will bend toward the higher refractive index. Okay, and you can also apply this to the second diagram. Here, our incident light is in the medium with a higher refractive index. And then when it reflects out to this upper medium with a lower refractive index, then it will bend along this direction because the N2, the N2 is higher than N1. Therefore, this light actually attracted to the higher refractive index medium. So you are not going to draw a line like this because N2 is higher than the N1. This bending can be true if N1, refractive index 1, is greater than the refractive index of 2. All right. Well, examples of the reflection are easily observed in our daily life. For instance, we have the coin behind the wall in the cup. Let me see if I can run this animation. Okay, so good, yeah. So, oops, sorry. Let me run this again. Sorry. So this incident light scattered by this coin, but unfortunately, this scattered light cannot reach my eye. So where this coin is actually hidden behind the wall, then we can actually reveal this coin by bending the light. Yeah. So we then fill the cup with the water, then the light will reflect it, and then when it comes out from this water, we can actually see there is coin behind the wall. Another interesting point is the appearance of this coin. Okay, let me switch it to a pen. All right, so the coin, which is located in the bottom, will appear above its object. So in other words, its apparent image formed above this object, and then I can find this location of this apparent image by introducing two lines. The first line, I'm going to extend my line of sight like this. And then I will also introduce a vertical line to this object. Yeah. Then at the intersection point, the image will be formed. Okay, so this is how you can find the location of the apparent image. Now, I have a couple of questions for you. So would you like to scan this QR code so that we can start the autocorrect questions, all right? So I'm going to also show you this autocorrect question pages. Just 1 second. Okay, so please scan this QR code to start the polling questions. So I will also scan it. Okay. So let's start. A parallel light rays cross interfaces from air into two different media, A and B. In which of the media is the light traveling faster? You can start the voting. So what do you think? So in which medium the light travels faster?
Why both medium A?
Oh, sorry. Well, yeah, this is, there is a typo. The second answer must be medium B. Should read medium B, all right? So medium A, medium B, or both the same. Very good. Thank you. Well, I'm going to close the vote in 5, 4, 3, 2, 1. Okay, so the correct answer is 1. I'm going to come back to those questions later. Okay, so for now, let me move on to the second question. So now parallel light rays cross interfaces from medium 1 into 2, then into 3. Now, what can we say about the relative size of the index of refraction of these media? So how do you want to answer to this question? Okay. I am going to close the vote in 5, 4, 3, 2, 1. The correct answer is 5. All right. So I'm going to explain those questions. So let me go back to the lecture note. Okay. So first of all, the light will travel faster in the medium A. So the correct answer is 1, the medium A. Why? Because, well, if you compare the light bending in the A and B, then you know that the B in the B, the light bends more. In other words, the refractive index of the B is higher than the refractive index of A. Then the light speed is reduced by the amount of the refractive index. Therefore, the light will travel faster in the medium A, whose refractive index is smaller than the B. All right. So the correct answer is 1. Now, in the second question, well, we are going to compare the light bending direction again. Okay. So when the light enters into the medium 2, you see that the light actually bend into the medium 2. In other words, refractive index of the 2 is larger than 1. So you can actually set this relation, all right? Now, when the light travels from 2 to 3, then you see that where the light now bend toward the medium 2 because the refractive index of 2 is larger. then our conclusion is where the index of 2 must be the largest, yeah? Then how are we going to compare those two mediums refractive index? The trick is you will ignore the second medium. Okay, and then directly compare the light bending of, light bending between the 1 and the medium 3. Then still the light bend, in the medium 3, light bends toward the medium 1. In other words, the index of the medium 1 is larger than the index of the medium 3. Therefore, the medium 2 has the largest index, followed by the index 1, and then the index 3. Okay. Any question on those the polling questions, or any other topics so far?
Prof.
Yeah.
The index of reflections of the media depends on the wavelength of the light, right?
True.
So that's why it causes the dispersion of the light when a spectrum passes through a medium.
That's a good point. So, but is this your question?
Yeah.
Okay. So, well, that's a very good point. So, first of all, the refractive index actually influence the wavelength. Okay, higher the refractive index, your wavelength is going to be reduced. And then we are going to talk about this in the week 3 when I introduce the wave. All right. And then when it comes to this dispersion, you're right. The refractive index will change, okay, with the different colors of the white light element. So depending on your wavelengths, depending on your wavelength, the refractive index also change. That's also true. And then I will come to that point in the next slide. All right. Okay. And is it okay with you? So can I move on?
Yeah. Thank you,
Okay,
Prof.
great. I'm very happy to hear your voice. And then, do you have any other questions before moving to the next topic?
Prof.
Yeah.
Prof, how do we
Yes.
tell which medium is greater than which medium?
In this question.
Yes, correct.
All right. So, well, refractive index of the medium 1 is the greatest. Okay. Followed by, the refractive index of the medium 2 is the greatest, and then followed by the medium 1 and then medium 3. And then you can come to this conclusion by comparing the bending direction. All right. When the light travels from the medium 1 to 2, you see that this bending actually, the light bends toward the medium 2 because the medium 2 has a higher refractive index. Okay, and then you will apply this to compare the index between 2 and the 3. And then when you want to when you want to compare the index between 1 and the 3, then the trick is you just ignore the intermediate, the medium. Okay, you just directly compare the light, the direction between 1 and then 3. And then you can also find that the light bends toward the medium 1. Therefore, the medium 1 has a higher refractive index than the medium 3.
Okay, thank you, Prof.
Yeah. All right. Any other question? So I'm going to also check the questions in the chat room.
Hi, Prof.
Yeah.
Is it possible for you to show the QR code again, because I exited the booklet?
Sure, but those two questions, the voting already over. But in the next set of the questions, I will flash the QR code again. Is it good?
Sure.
Okay, great.
Thank you, sir.
All right, thanks. Any other question?
Hi, Prof. Can you hear me?
Yeah.
Yeah. In the LAMPS activity and lecture, you mentioned that the light bend towards the normal because or after the light travels from a dense to a less dense material, and then you are pulled towards the denser material because of gravity. How much of like effect gravity plays in this? Like,
sorry,
what
well,
does it
I just, yeah, it's not because of the gravity. Sorry if it's, it might be a bit confusing. I just portray, okay, I just use, illustrate the bending, okay, to the gravity force. So when you consider the gravity force, the heavier object, okay, attract the, I mean, has pull the other objects with a much stronger force. And then you can actually apply this to determine the bending direction when it comes to the refractions. So the medium with a higher refractive index will pull the light as the gravity force. So there is no gravity force to come into play. I just will illustrate this light bending direction as a pulling force, as a gravity force. But they are not related, all right? Sorry about that if it was confusing.
Prof,
Yeah.
we cannot portray this as a gravity force because if there was a gravity force that pull, or other forces that pull the light into the mediums into the normal, then the light will be moving faster in the medium because of the pulling force.
Yes, you're right. So again, if it's confusing, sorry about that, but I'm not going to say that the gravity force is acting on the light bending in our context. Okay. All right, and then any other question? Otherwise, let me move on to the next topic. Okay. So now we are going to learn about this chromatic dispersion. So here, where we have this diagram, the white light entered to this glass prism, and then as soon as it entered to the glass prism, then it actually split into this rainbow color, right? And then from this observation, what can we, what shall we, how can we explain the splitting of the light, and then what's the implications that we can derive from this observation? So in order to define this chromatic dispersion, and then I'm going to use my notepad, okay, draw some diagram and then make some conclusion. So let me switch to the my notepad, just 1 second. I'm going to open my notepad. Right. Okay. All right, so what I'm going to do is, well, I will copy the same diagram in this notepad, all right? So we are going to have this prism, all right? And then we have the incident light. Then, well, this incident, oh, sorry. Then this incident light will spread into the rainbow color with the red color on the top and blue color in the bottom, and then they will reflect out to the air like this. Okay, and so we have a reflection in this diagram, and then I will look into the very first reflection. Okay, so because we have two colors, red and blue, therefore I can define the reflection angle for the red color and the blue color separately. So my angle of reflection for the red is going to be this, and then my angle of reflection for the blue color is going to be defined as this. Okay, again, the angles are measured from the normal line to the respective rays. And of course, my angle of incidence is going to be defined here. Now, what I'm going to do is I will set the Snell's law, because of this is the reflection. So I'm going to set a Snell's law equations for those two, the red and the blue colors. Okay, so let me first set the Snell's law for the red color. So I'm going to use the red color, and then the Snell's law will be written as N1. So again, I forgot to define the index. So index of the outer medium is N1, and index of the glass is going to N2, right? Now, for the red color, our Snell's law goes like n1 sine theta 1 equals n2 sine theta 2 red. And I can also set this Snell's law for the blue color, which will go n1 sine theta 1 equals n2 sine theta 2b. Now, if you compare those two equations, then you can come to this conclusion. Well, because they share the same the common terms n1 sine theta 1, which means n2 sine theta 2r equals n2 sine theta 2b. Now, in this equation, you know that this refraction angle of this red color and then refraction angle of the blue color are different. Yeah. So from our observation, we know that they are different. Then, in order to satisfy this equation, then we must conclude that the index accounting for the red color is different from the index accounting to the blue color. So I'm going to introduce those R and then B to differentiate those two refractive indices. Now, this clearly suggests the dispersion, okay, of the light in a glass. So our conclusion is this: although the light travel in the same medium, okay, depending on their color or their wavelengths, they experience different refractive indices. In other words, the red color and the blue color will travel at different speed in the glass. Okay, so that's called the chromatic dispersion. So I will go back to the lecture note to continue. All right, so from this observation, we come into two conclusions. Yeah. So the first conclusion: the white light consists of many colors, and the different colors have different indices of refraction. So, in other words, the refractive index depends on the wavelengths, and this is a dispersion. And in this diagram, actually, will illustrate this dispersion of the common materials in our daily life. So while this x-axis is the refractive index, the x-axis is our wavelength, and the y-axis is the refractive index. Now let me have a look at pick up this fused quartz, which is the glass. The glass has higher refractive index for shorter wavelengths, and then the index gets reduced along the wavelengths. And I'm going to read this first bullet point. In general, the index of the refraction for given medium is greater for shorter wavelengths than for the longer wavelengths. In other words, when white light entered the dispersive medium like glass, then the blue light, the blue color will bend more than the red color, because the blue color experience higher refractive index. Okay. So one example of this chromatic dispersion in our daily life is actually the rainbow. Now, the sunlight can enter to the water droplet, and because of the dispersion, the sunlight will split into the different colors, the rainbow colors, and the red color and the violet color will refract at different the angles. Therefore, when they come out from this water droplet, they will where they are in the different they will take the different paths because their angles are different. Therefore, when we look at the rainbow, the red color is always on the top of the rainbow, and then blue is in the bottom. Okay, because of this dispersion, and then the corresponding refraction angles are different. All right. Now I will move on to our last topic, which is the total internal reflection. Okay. Now, let me use this diagram. In this case, we assume that the light source is in the medium with higher refractive index. In other words, this lower medium has a higher refractive index than the upper medium. Then where we can consider that this lower medium is water and the upper medium is air. All right. Now the light from this source first strike this boundary. Then what would happen? The part of light will be reflected, and then part of light will be reflected out to the air. Right. Now this is what I'm going to do. I am going to increase the angle of incidence. Yeah, so I'm going to increase the angle of incidence at this. Then what would happen to this reflection? Well, if it's difficult to imagine this angle of reflection, we can always start with this the Snell's law. Yeah, so I'm going to draw the Snell's law, and one sine theta 1 equals N2 sine theta 2. Okay, so again, what I want to do is I want to increase this angle of incidence. So then what would happen to the refraction? The refraction angle will also increase correspondingly. Yeah? So if I increase the angle of incidence, then angle of refraction always increase too. Now, what would be the maximum angle for the refraction? The maximum angle of refraction is going to be 90 degrees. Yeah, the refraction cannot be any larger than 90 degrees. Then well, any refraction larger than 90 degrees means that there is no refraction. Indeed, that happens when you reach to this specific angle, which is denoted as angle theta c. Then our refraction goes along this boundary with the 90 degrees of angle of refraction. And then if I increase this incident angle beyond this critical angle, then all the light will be reflected back to the original medium, the first medium. And then this is called total internal reflection. Okay, so when the incident light angle, the incident angle goes beyond this critical angle, then all the light will reflect back to the original medium through this total internal reflection. And well, we can actually derive the mathematical expression for this critical angle starting from the Snell's law. Yeah? So Snell's law, according to the Snell's law, where we can set this equation N1 sine theta c for the critical angle equals N2 sine 90 degrees. And then again, 90 degrees is the reflection angle at the critical angle. Yeah, and the sine 90 degree is 1. So this becomes N2. Now, we can write this for the sine theta c. Then this sine theta c simply becomes N2 over N1. In other words, if we are given those two refractive indices, then we can always come out with this critical angle for the total internal reflection. Okay, of course, this angle theta c is going to be arc sine N2 over N1. All right. So as if the incident angle gets greater than the critical angle, then we can generate, or we can induce this total internal reflection. The most successful application of this total internal reflection is actually the optical fiber, which support our internet today. Well, let's say we have an incident angle with a sine theta I, which will reflect into this glass medium, and then this reflected light now become an incident light to this second interface. And at the if this incident light strike at the critical angle, then we can realize the total internal reflection. from this diagram, you can easily see that this critical angle condition is actually related to the first incidence angle. Okay, in other words, this critical angle or the occurrence of the total internal reflection is determined by this incident angle. Okay, and this incident angle is called acceptance angle. In order to achieve total internal reflection, the first incident angle to this glass must be smaller than this acceptance angle. All right. Then we now have another definition, which is called numerical aperture. Numerical aperture is sine of the first incident angle, and then this is determined as the square root n1 square minus n2 square, where the n1 is refractive index of the core material, and the n2 is the refractive index of the clouding medium. Okay, and you can actually derive this numerical aperture from this diagram using this relation. So I would encourage you to derive this numerical aperture from this diagram and then this the trigonometric the relation. All right, now I think we are ready to have a few more the would-like questions. So would you like to scan this QR code? And then I will also switch my screen to these would-like questions. All right. So please scan this QR code to join this voting. So let's start with the first question. So total internal reflection happens when light is incident from lower refractive index to higher refractive index. So is this true or false? Okay, very good. I'm going to close the vote in 5, 4, 3, 2, 1. Okay, the correct answer is first. All right, so let me move on to the next question. Well, to shoot a fish with a gun, should you aim directly at the image, slightly above or slightly below? So how do you want to catch the fish? Okay. Do you aim at the fish or slightly above or slightly below? I'm going to close the vote in 5, 4, 3, 2, 1. The correct answer is 3. You must aim slightly below. Now I will show you the next question. Now we use laser gun, okay, instead of the actual gun. Then where do you want to aim to catch the fish? Directly at the image, slightly above or slightly below?
What's the wavelength of the laser?
We don't consider the wavelength. Let's stay away the laser to shoot light. Okay, I'm going to close the vote in 5, 4, 3, 2, 1. Yeah, the correct answer is 1. Now I will move on to another question. So two colors of light AB originally travel in the same direction in the air, now sent through a glass prism. the color A changes direction more than B. So which travel more slowly in the prism, A or B? So I will close the board in 5, 4, 3, 2, 1. All right, the correct answer is 1. Okay, well done. Now, this is going to be the last question. So 5 rays enter glass prism from the left, and then we can rotate the prism, and then if you want all the 5 rays experience total internal reflection, then do you want to rotate the prism clockwise or anti-clockwise? All right. We want to move it clockwise or anti-clockwise? Yeah, I'm going to close the board in 5, 3, 4, 3, 2, 1. The correct answer is 2, anti-clockwise. So, well done. Well, I'm very happy that most of you actually answered correctly for all those questions. So let me go back to the lecture note so I can briefly describe those, briefly explain the answers. Right. So, TIR happens when the light is incident from the low index to the high index, which is first. You cannot actually make the total internal reflection with this condition. Well, we can understand this with this critical the angle condition. So our critical angle, so sorry, sine. Oops, my writing gets a bit more early. So let me try to draw S. All right. So sine angle theta sheet, the critical angle is defined as N2 over N1. Okay. Now here, if our refractive index N2 is greater than N1, then this sine theta is going to be larger than 1. Which is not true yet. This cannot be true. So we cannot have this condition. Therefore, the light, the incident light must be in a medium with a higher refractive index to realize the total internal reflection. So the correct answer is the first. Now, our second question. So we need to aim slightly below because of the refraction, the apparent image appears above the actual object. Therefore, you should aim slightly below, okay, the apparent image. Now, when we use a laser gun, the laser gun also were affected by this refraction. In other words, laser beam will reflect inside this water. Therefore, we must aim this apparent image to compensate the light bending. Okay, so the correct answer is aim at the image. Now, we consider two colors A and B, and then color A change direction more than B, which means color A experience higher refractive index. Therefore, its traveling speed is going to be slower than the B with a higher, with lower refractive index. Therefore, the correct answer is A. Okay, so light carrying higher refractive index will travel slowly. Yeah? Now, finally, where we have these 5 rays entering to the prism glass, and then we must rotate the prism anti-clockwise to make all the the 5 rays experience a total internal reflection. And then I think it's best to draw some diagram to answer to this question. So let me switch to my notepad. Okay. All right, so I'm going to draw this prism, and we have the incident light coming into this direction, and then this will reflect to the slanted glass, slanted interface, and they reflect out like this. All right, now if I rotate this prism anti-clockwise, so here, first of all, I can define the angle of incidence to this slant, the surface edge this. So this is going to be my angle of incidence. Now, if I rotate this the prism anti-clockwise, then my new slanted surface is going to be drawn at this. Okay, and its corresponding vertical line is also going to be drawn as this. Then my angle of incidence will be defined here. And obviously, the angle of incidence with this anti-clockwise rotation is larger than the original angle of incidence. And then in our total internal reflection discussion, I already showed you that we must increase the angle of incidence to reach the 90 degree of the reflection angle. Therefore, this is the right choice to rotate anti-clockwise this prism so that we can increase the incident angle to the slant surface. So the correct answer is anti-clockwise. All right. Now this is the end of the lecture. And there are more questions in the LANs, in the NTU LAN, and then this lecture slide will be available in the NTU LAN. So I'm going to upload this to the NTU LAN, all right? And before closing the lecture, do you have any question?
Prof?
Yeah.
You said that the total internal reflections occurs beyond the critical angle.
Yeah.
So there's no reflection, only the reflection. No reflection, only the reflection.
So beyond this total internal reflection, there won't be any reflection. So all the light will remain in the first medium.
So that means the Brewster angle cannot be beyond the critical angle, right?
Okay. So that's a good point. And I can say yes, but we will discuss this in the last week when I introduce the polarization.
Okay,
great. So
yeah. I have a question.
Yes.
So when the angle of refraction of a light ray is exactly 90 degrees, is it considered total internal reflection or refraction?
So that's a good question too. In our context, this condition, okay, the total the critical angle also were considered as the total internal reflection. So when the incident angle strikes this critical angle, we consider this is also total internal reflection. So when you want to answer your question, when you want to answer in this kind of question, you can say that this angle, okay, must be greater than critical angle or equal. Okay, so it's a bit gray area, but in our the class, I will consider this critical angle also the total internal reflection. So as long as the refracted light does not escape from the first medium, I will consider this as a total internal reflection.
Okay, thank you both.
All right, thanks. Prof. Yeah.
Never mind. Zheng Hui, go ahead first. You sure? Okay. Prof, I want to ask you something about mirrors, because
Okay,
from
about-
what I read out in some books, right, mirrors actually have a reflective index also, like plane mirrors itself.
Okay.
So it somehow doesn't actually how do I put it? It doesn't actually make sense now, because you know that mirrors actually reflect instead of refract, right?
Yeah.
So while I'm reading, I'm a bit more confused also. So can you explain why does mirror actually have refractive index also?
So any material has its own refractive index.
Yes.
Yes. Therefore, even mirror, while they have a refractive index.
Yes, but
yes. So
when
the function of the mirror is reflection. It just will bounce back the light.
Correct.
Yeah. Therefore, we don't really worry about the refractive index of the mirror material.
Oh, so okay, from what I read actually is that the mirror actually have a refractive index of 1.6.
Mm-hmm.
So it's like, okay, if it's 1.6, doesn't that mean that when the light actually passes through the mirror, it will actually bend inwards? Correct?
Yes, but what would you say if what do you think if the light first bounced back before experience any significant the reflection?
Oh.
Wait, Prof, then isn't that considered total internal reflection?
No.
No.
No, it's not.
Total internal reflection must be understood in the context of the reflection. So we use the Snell's law to explain the total internal reflection. Okay, but when it comes to the mirror, there is no such Snell's law. It's just where the light just bounces back.
Okay.
So we use the law of reflection, where the angle of incidence is the same as the angle of reflection.
Okay. A bit still not there, but okay.
Okay, so
I kind of get it.
Yeah. So if you have any other questions, still have the same questions, then you can actually come to me later.
Okay, sure.
All right.
Prof, in optical dispersion, when the red and blue light disperse, they have the same frequency, right? Since the source of light is same, only wavelength is different, right?
Yeah, that's a good point. Yes. Their frequency remain the same, but only the optical, the wavelengths change.
Thank you, Prof.
Thank you.
Hello, Prof.
Yeah, any question?
Hello, Prof.
Yeah, I can hear you.
Prof.
Yeah.
Can I ask, how does the wavelength affect anything?
Sorry?
The wavelength. How
Uh-huh.
does the wavelength affect anything? Wavelength is like the distance that the light travels, is it?
Wavelength is the length that light oscillate one cycle.
Oh, okay. Because if let's say the question give you like two wavelength, that means the light actually split into two, is it?
Light oscillate twice. So like a sine wave,
okay.
oscillate once, then it's one wavelength. If it oscillates twice, then it's two wavelengths.
Because I got this question in the tutorial, right, where they put there got two wavelength. Then after the tutorial teacher say that the light split into two. The refraction, there's two of them, two light. Is it correct?
I'm not sure which sort of question you refer to, but if you want to differentiate the two waves based on the wavelength, then you must measure the length of the wave itself. So if one oscillation finishes in the 1 meter long for wave one, and then the other wave finishes this one oscillation in 1.5 meters, then they are two different waves.
Oh, okay.
Yeah, but
Because
if those two waves, okay, coming to the same wavelength. For instance, first wave oscillate, finish one cycle in 1 meter, and then the other occasion, this wave oscillate twice in 2 meters. Then actually they are the same waves.
Oh, okay. Because what I seen in the question is that we were given two wavelength, 400 nanometer and 700 nanometer. Then with these two wavelength, we were given two different reflective index. Yeah. So now I see that the light split into two. That's what I see now.
Yeah, light split into two. Yeah, that's correct, because I guess the light actually travel inside the glass. Yeah, so they will split into two the colors.
This is because of the two different refractive indexes due to the two different wavelengths, right?
Due to the dispersion.
Huh?
Due to the dispersion.
Oh, dispersion. Okay.
Yeah.
Okay. Thanks, bro.
All right. Thank you.
So hello, Prof. Can you hear?
Yeah.
Okay. Got three questions. This one, right, is for the derivation for the wait, let me see, the slide 16, I think.
Okay.
Oh no, slide 15. The derivation for the Fermat's principle. Is it necessary that we derive this, or it's just an extra knowledge that is like good to know?
Yeah, it's good to know.
Okay.
And then it's not difficult at all.
Okay.
Okay.
Okay. Then for the other question is, okay, since you say in this course that at critical angle it is considered as total internal reflection. So actually in reality, how to say, it's technically not, right?
So in practice, when we design the lasers, for instance, for the optical communication, we always design the instant angle or the critical angle, the instant angle larger than this critical angle. So we will have this condition for optical communication rather than this case, because this will guarantee you less loss.
Okay, so technically we could say like it has to exceed to, like, how to say, for the definition that I learned before, it was like it has to exceed critical angle.
Yeah.
Okay.
Yeah.
Okay, then
but you can consider this as a kind of my offer. Okay. So by right, also in practice, in order to have the total internal reflection, your incidence angle must go beyond the critical angle. Okay. However, I also know that many of students actually treat this critical angle as the instant angle for the total internal reflection. And if you saying so, even if you're saying so, I'm not going to deduct your mark.
Oh, okay.
Okay, so it's just try to help you. So I know that you understand the physics. Okay, but I don't want to penalize you because of those small things.
Can. Yeah. Okay, then for the optical path length, it is not actually like a measurement length, right? It's actually describing like the time taken for the.
Right. Yes, absolutely.
Alright. Okay. Then one last question. Okay, of course the tutorial, I think question number 5. Okay, I forgot how the question looks like, but it's something like a ray of light enters a medium, then after that exits the medium. So they are trying to say that the light of the angle of the light entering, prove that the angle of the light entering is equal to the angle of the light leaving. Okay, you get what I'm trying to say? Okay, so it wasn't clear in that particular tutorial question, but if in exam this question will ask, right? Do we have to assume? Do we have to write out that we assume that the surfaces where the light enters and leaves that particular medium are parallel?
You should understand that part. And then for your information, in the tutorial questions, I also compile relevant past exam questions. And then the first past exam question actually asks you derive that condition.
Yeah.
But
is like how to say, like if let's say the question did not say that, but from what I remember is
all right.
It has to be one of the conditions.
Yes. Yeah. I don't want to be very harsh.
Oh, okay. But okay, like just for the accuracy lah. Okay, thanks. That's all.
Okay. Any other question? Well, I have some questions in the chat room, so let me briefly go through those questions in the chat room. First of all,
Prof, I have a question.
Yeah.
Okay, regarding if let's say your critical angle, is it possible for total internal reflection as well as refraction to occur simultaneously?
No.
Okay, thank you.
All right, thank you. So I will go to the chat room questions. Okay. So first of all, is the lesson recorded? Yes, it's being recorded. And then I will let me see. Well, I think I can stop the recording now. And then I'm going to upload this recorded video